This lecture is part of an online course on mathematical group theory and will be about the transfer homomorphism between groups. So as motivation for this, in previous lectures we've classified the groups of order up to 24, and we're now going to look at the groups of order 30. So group of order 30 has order 2 times 3 times 5, and this is the first example of an order that's a product of 3 different primes. And in order to do this, we're going to show that if G is order 30, then G has a normal subgroup of index 2. And the way we will do this is we will construct a transfer homomorphism from G to its a subgroup of order 2 of it. And this map will turn out to be onto. So here this is a Selov 2 subgroup of G. And this map will be onto, and so its kernel would be a normal subgroup of order 15. This makes G easier to classify because the only subgroup of order 15 must be cyclic of order 15. So we get an exact sequence like this. And this is split because G has an element of order 2. So G is isomorphic to a semi-direct product Z modulo 15Z with Z modulo 2Z, and these are just classified by the ways the group of order 2 can act on the group of order 15, and there are 4 ways you can do this, and this gives us 4 groups for G, none of which are terribly interesting. It can be cyclic, or it can be a product of a group of order 2 by group of order 3 by a cyclic group of order by the dihedral group of order 10, or it can be a product of a group of order 5 by the dihedral group of order 6, or it can be the dihedral group of order 30. So there's nothing new, they're all just products of groups we already know about. So what we've got to do is to construct this magical transfer homomorphism. So I should say this is transfer. And the way it works is as follows. Suppose H is a subgroup of a group G, then the transfer homomorphism will be a homomorphism from the abelianization of G to the abelianization of H. So what is the abelianization of G? Well, this is the biggest abelian quotient of G. So informally, you can think of it as being what happens if you take a group and force it to be abelian. So what we do is we take the set of all elements a, b, a to the minus 1, b to the minus 1 in G, and these generate a subgroup called the commutator subgroup of G, sometimes denoted like this, because A, B sometimes used to mean A, B, A to the minus 1, B to the minus 1. So, and G modulo the commutator subgroup is abelian because you've kind of forced all the elements to commute by just quotienting out the bits that stop everything commuting. If you have any homomorphism from G to an abelian group, then you can easily see that this actually factorizes through the abelian quotient of G. So this is a sort of universal way of making G into an abelian group. And what you notice is we seem to have made a mistake here because this arrow goes in the wrong direction. It seems to be going in the wrong way. So if we've got a map from H to G, then it's pretty easy to see we've got a map from we get an induced map from the abelianization of H to the abelianization of G. So it looks as if I made a mistake there. But in fact, the transfer really does go the wrong way. The way of defining the transfer we're going to give looks a bit mysterious. The most natural way of defining the transfer is to use the fact that the abelianization of G is in fact some sort of Tate homology group of G with coefficients in Z. And there are various Tate cohomology groups for all integers n. And for all of these Tate cohomology groups, you get a map from the Tate cohomology of group of G to the Tate cohomology of H. However, using this definition requires defining Tate cohomology, which takes rather a long time. So what we're going to do is going to forget about Tate cohomology and come up with a sort of elementary ad hoc definition, which looks a bit mysterious. This is sort of the definition you get if you unwind the definition of Tate cohomology. So we define it as follows. This is the definition of the transfer from the abelianization of G to the abelianization of H. And what we do is we write G as a union of left cosets of H. So it's a union of elements AIH. And then we're going to look at what, let's pick some G in G and look at the action of G on all these left cosets. So you remember G is really acting on the set of left cosets by left translation. So let's look at the action. Well, suppose these left cosets are A1H, A2H, and so on. Then we have GA1 is equal to A, well, it's going to be A something. Let's say AI1 times H1. GA2 will be AI2 times H2, and so on. So the action of G on these left cosets is it's taking A1 to AI1 and A2 to AI2, and so on. And we have these undetermined factors of H on the left. And then the transfer of G is simply defined to be the product H1, H2, H3, and so on. And this definition looks really fishy. So we better check that it is actually a well-defined definition. First of all, the order of the HI does not matter. You see, we've got H1, H2, H3. Well, why don't we take H2, H1, H3 and get a different element? Well, the order doesn't matter because we're considering this to be an element in the abelianization of H. So whatever order you multiply these in, it gives the same element in here. So as we work in H, abelianization of H. So the order doesn't matter. Well, the next problem is A1 and A2 and so on aren't uniquely determined. So what happens if we change A1 to, say, A1H, because A1H is equal to A1H. So the definition of transfer seems to depend on our choice of left coset. Well, it doesn't. Actually, it doesn't, because we know that GA1 of H is now going to be AI1 H1 times H. Sorry, there shouldn't be a 1 there. And we've also got a GA AJ for some J is going to be A1 times HJ. And this will be equal to A1H times H to the minus 1 HJ. So if we replace A1 by A1H, then we replace H1 by this, and we replace HJ by this for some J, where J is the thing mapping to A1. So we replace H1 HJ by H1H, H to the minus 1 HJ. And this is just equal to H1 HJ. So the choice of coset representatives doesn't matter. So T does not depend on the coset representatives AI. So it is actually well defined. Finally, we want to check that T is a homomorphism from G to H abelianized. And for this, we just calculate what it does. So suppose GA1 is equal to AI1 H1, GA2 is equal to AI2 H2, and so on, so that T of G is equal to H1, H2, and so on. And suppose we've got another element, G prime of A1, which is going to be a J1, H1 prime, G prime A2 is equal to a J2, H2 prime, and so on. So T of G prime is equal to H1 prime, H2 prime, and so on. Now we have to work out what G prime G does to things. Well, this takes A1 to AI1 H1, which is now going to be A something or other, whatever G prime takes A1 2 times H I1 prime times H1. And similarly, G prime G of A2 will be A something or other H HI2 prime H2, and so on. So T of G prime G is the product of all these. So it's HI1 prime H1, HI2 prime H2, and so on. And now you notice that these things here are just a permutation of these things here. Sorry, these things there, not that one. So T of G prime G is just the product of all the H primes and all the H's. So it's the product of T of G and T of G prime. So this equals T of G prime. So we verify that this rather peculiar definition of transfer is indeed a well-defined homomorphism from the abelianization of G to the abelianization of H. Incidentally, we define it using left cosets, and you may wonder what happens if we define it using right cosets. If you define it using right cosets, you get the same thing, but I don't need that, so I'm not going to bother proving it. Well, the next question is, how do you calculate it? So if G is in G, let's try and find out what is T of G. And the definition makes it not easy to see what this is. Well, so let's try. Let's take G to be in H. So this makes it a little bit easier to calculate. And then we calculate GA1 is going to be A2. And what we're going to do is just choose A2 to be equal to G of A1. You remember we could vary the choice of cosets without changing the transfer homomorphism. And similarly, GA2, then we can just choose A3, and it goes on like this until we get back to A1. But then we can't choose A1 because we already fixed A1, so there has to be some element H here. Let's call this H1. And then we can carry on like this. GAN plus 1 is equal to AN plus 2 all the way up to GAN plus K is equal to AN plus 1 times some element H2. So we can, what we're doing is we're splitting up the action of G on the set of cosets into cycles. And for each cycle, we just get one element of H, and then the transfer of G is going to be H1, H2, and so on. Well, how does that help? Well, what we do is we notice that G squared A1 equals A3, G cubed A1 equals A4, so G to the N A1, and you go all the way, is equal to A1 H1. How does that help? Well, this says that H1 is equal to A1 to the minus 1 G to the N A1. And similarly for H2 and so on. So H1 is actually a conjugate of G to the N. Well, how does that help? Now suppose H has the following special property. Suppose that in H, no two distinct elements are conjugate in G. Well, then from H1 equals A1 to minus 1 G A1, you notice these are both in H and they're conjugate. So this gives us H1 equals G, and similarly H2 equals G, and so on. So, sorry, G to the N, and this would be G to the whatever the next number is. So that should have been G to the N. So the transfer of G is just equal to H1, H2, and so on, which is equal to G to the N, G to the K, and so on, which is equal to G to the number of cosets, which is the index of H in G. So we've actually found a formula for the transfer of an element of H, provided H has this slightly funny property here. Well, when does H have this property? Well, first of all, if G is abelian, then the transfer of an element of G for G in H will just be G to the G, the index of G in H. So it's not really a terribly exciting map. This also occurs if H is in the center of G. And another case that occurs if H has order 2. Because if H has order 2, then any two elements in H that are conjugate must obviously be the same, because they're either the identity or they're the unique element that's not the identity. So in other words, if H is order 2, this means that the transfer from G to H acts on H as G goes to G to the index of G in H. Now, if this is even, then that's rather uninteresting. It just says the transfer is the trivial homomorphism. But if G modulo H is odd, this means that the transfer map from G to H, which is equal to the abelianization, is onto. So in other words, if the order of G is of the form 2n with n odd, then there is a homomorphism given by the transfer from G to H, where this is a Selov 2 subgroup. I said this is a homomorphism T onto H. So G is a semi-direct product K with H, where this is index 2 and this is a group Z modulo 2Z. So we found the structure of all groups of order 2 times an odd number. They're all semi-direct products of a group of order 2 and some group of odd order. So in particular, G is not simple. So there are no simple groups of whose order is congruent to 2 modulo 4. And of course, in particular, we can apply this to the group of order 30 that we started with and see that it has a normal subgroup of order 15, as we said earlier. So we can do a bit more than this. So suppose P is the smallest prime dividing the order of G. If P squared does not divide G, then the CEL of P subgroup is Z over PZ. And you notice that no two distinct elements can be conjugate. Because if they were conjugate, they would have to be there would have to be an inner automorphism of G acting on this non-trivially, and the group of inner automorphisms of this is only divisible by primes less than P, but G doesn't have any elements of order less than P. So the transfer map from G to Z over PZ acts as G goes to G to the G, the order of G over P for G, sorry, little g in Z modulo PZ. And since this is co-prime to P, this transfer map is onto. So G has a normal subgroup of index P. We call that a normal P complement. So G is not simple. In fact, if you look at this argument a little bit more carefully, you see that it also applies even if P squared does divide the order of G, provided the CEL of P subgroup is cyclic. So in particular, we found that if so for any simple group, its order must be divisible by the square of some prime. In particular, it must be divisible by the square of some prime, not dividing it. So let's give one final application of the transfer. So suppose G is simple, and suppose that the CEL of 2 subgroup of G is, well, it can't be Z modulo 2. So the next simplest possibility is that Z modulo 2Z times Z modulo 2Z. So it's got 3 different elements of order 2. And the question is, are these conjugate in G or not? Well, then all elements of order 2 in G are conjugate. Well, suppose not. Then look at the elements in the 2 CEL of subgroup. We've got an element 1 and we've got 3 elements A, B, and C. If these aren't all conjugate, then either no 2 of them are conjugate, or maybe A and B are conjugate. We don't really care, but there's going to be some element C not conjugate to anything else. So then some element C not equal to 1 in Z over 2Z squared is not conjugate to anything else. Now we look at the transfer map from G to Z over 2Z times Z over 2Z. And the transfer of this element C, as before, is equal to C to the order of G divided by 4, which must be equal to C because this is odd. So we've got a homomorphism from G onto a group of order 2 or 4. So G has a normal subgroup of index 2. So G is not simple. So you see that's the transfer map has given us a small amount of information about simple groups. If the CL2 subgroup is the Klein 4 group, then all involutions in G are conjugate. Okay, the next lecture will be about what a ridiculously large number of groups of prime power order there are.